We heard already the term Vadose zone. We heard about the term critical zone, soil. So all of these are somewhat confusing if they're not put in context. So let's just clarify what are we talking about. The Vadose zone, in general, is a zone between the Earth's surface and the water table. In many humid areas, it is synonymous with the depths of soil. So people say soil, Vadose zone, they actually mean the same thing. But when you go to desert areas in which water tables can be a few hundred meters below the surface, so the part that is unsaturated, or the near surface unsaturated part of the Earth, is called the Vadose zone. And the soil may be only a very thin mantle of a few, maybe half a meter or meter above that Vadose zone. Okay? More recently, people were interested in putting this domain in a global context, and they define a new name. They call it a critical zone. You know, it's ever more sensational and exciting. And basically, they extend the Vadose zone to the top of the trees and look at the exchanges between the top of the canopies and the atmosphere and terminate it at the bottom, again, at the water table interface. So really, these three terms are somewhat synonymous, not always, because the critical zone people are more interested in large-scale processes, also at long time scales of soil formation. So it is a bit justified to have this proliferation of terminology. But now that we clarified it, we all talk about the zone in which we have coexistence of gas, liquid, and solids in the subsurface. Okay? The importance of this coexistence is it cannot be understated, because that gives rise to a very unique compartment of the biosphere in which life is simply exploding or flourishing. All our plants, forests, most of the biomass of the planet, and there is a recent paper that kind of puts it in numbers, is fed and anchored in this near surface Vadose zone or soil. So it is a zone of great importance, so the critical zone term is actually quite appropriate for it. Now, yesterday we heard from Jesus a definition of head and potential, and also earlier on today, and I'd like to kind of clarify it so it is completely clear what are we talking about. So we are talking about the energy state of water as it enters a soil, either spontaneously or by application of water from rain or irrigation and so on. And the fact that we have to define the energy state of that water relative to a reference state. So I have this very sophisticated experimental device, a water container at a reference state. When I introduce a porous medium, this paper towel, in contact with the water will move from this reference state to the porous medium spontaneously. I'm not doing any work to move the water. And now this water that was in the free state is held in the porous medium. Its energy state is lowered. How do I know it's lowered? Anybody? Sorry? It's spontaneous, and in fact, to get the water back to the reference state, I have to apply work. Okay? So basically, that interaction between the water and the porous medium, or the energetic of that, is encapsulated in the definition of the soil water potential. We have several factors that affect the soil water potential. For example, the position in the gravitational field, whether this is on the top of a hill or a bottom in a valley. We have a component that is completely due to interaction between the water and the solid matrix. We call it the matrix potential, and we come back to that. I'll also call it the capillary potential or the capillary pressure to satisfy my colleagues who want to call it this way. We have the pressure potential that Jesus talked about yesterday that drives groundwater flow. It's a positive pressure. And in some cases, when we have membranes, we have an onset of a solid potential that basically add to, as Reen mentioned earlier, to the stress of the plants. Okay? So all of these are summed together into a total water potential, and differences in total water potential in space will drive flow. So that's the notion of a gradient, the differences in potential in space. Okay? So that's basically the formal definition is the amount of work that infinitesimal amount of water is at equilibrium is capable of doing when it moves to a standard reference. So basically, you bring a bucket of water to the top of a hill, you can generate electricity if you let it run downhill. Okay, so that the notice here that we were careful not to define what is this amount. So this amount can be energy per unit mass, energy per unit volume, or energy per unit weight. Engineers like the energy per unit weight because the dimensions are length, so we have this dimension of head. But energy per unit mass or volume are equally valid. Basically, the relationship between these forms are given between the relationship between mass, volume, and weight. And this little equation here, if you remember it, it will help you move from if somebody reports values of potential at joules per kilogram, you basically divide it by G and you get units of length, or if it's in units of, if somebody is using dimensions of pressure, you divide by the density, or sorry, you divide by rho G and you get the units of head in terms of, in dimensions of length, okay? So far, it's all clear. So these are the players in this field. And I'd like to focus now, the rest of my talk, on one component of the water potential, and that's the metric potential. So the metric potential is extremely important in the unsaturated zone, and it is a phenomena that, or a type of interaction that happens when you have air in the case of water, because it will also appear in other fields. When you have air and water and held in the same porous medium, in other words, when the system is unsaturated. It results from interactions that are of capillary nature, and I explain what is, but also of adsorption of liquid on surfaces. And we, unfortunately, cannot yet distinguish clearly between these two contributions to the metric potential. So when we talk about the metric potential, we talk about a collection of interactions that sometimes will be dominated by capillary processes. In other cases, they'll be dominated by adsorption. And I'll try and clarify the differences between those. So what are the factors that affect the metric potential in soils? I grouped them in some almost arbitrary grouping. Some of them are due to surface tension phenomena. Others contributions are due to contact angle and wettability. Surface roughness will play a role, and you can put it as part of interfacial processes or part of geometrical factors. I put it in here, and I'll explain why. Geometrical factor, we have curved interfaces, we have pore spaces, and in them we'll have capillarity, the classical way we understand it. And at the end, there'll be additional interfacial processes that are associated with adsorption. Okay? So let's go to the top of the list and talk about surface tension. So when you look at the surface of water, in general, water itself is a kind of a flickering crystal. It has in it, it is made of a polar molecule. By polar, I mean that the electrons spend more time orbiting the oxygen than they are the hydrogen. So the oxygen will always be slightly, have a slight deficient or negative charge, whereas the hydrogen will be slightly positively charged. This is not permanent charges. This is just, this is our kind of a spatial distribution of the electrical field around this, molecule. And that gives rise to formation of a short-lived bonds between the slightly positive and slightly negative of this molecule, and these are called hydrogen bonds. They are benign in the sense that they are not very strong, but they are super important in the properties of water the way we understand it. So in general, this picture here is the general types of bonds that the water molecule will have in the bulk. Roughly 4 molecules on average. They don't last long because they constantly break and rebond based on kinetic energy and other factors. However, at the interface between the air and the water, or between the water and other vapor, we have an imbalance of these hydrogen bonds. I would say on average we have 3 bonds at the surface. So bringing a new molecule to the surface is energetically unfavorable. I have to break a molecule with 4 bonds and bring it to a surface with 3 bonds. And that gives rise to the phenomena of surface tension, in other words, a surface that feels like a membrane, that would like to reduce its area as much as possible, and increasing it, in other words, bringing more and more molecules to the surface, costs energy, and we'll explain what that cost of energy. So, in terms of energetics, first of all, the surface tension itself is expressed as energy per unit area, joules per meter square, or force per area. It's basically the same thing, which means that to increase the area by 1 meter square, I have to invest 0.07 joules per meter. Sorry, it depends on the units that I selected here. So, in other words, there is a fixed point to increasing the surface area. This is quite different than a membrane of a balloon or some other elastic membrane that obeys Hooke's law, that the more you stretch, the bigger the force. In this case, the energetic coin is fixed. Okay? So there are different fluids that can also create this or give rise to this surface tension. Alcohols here. Mercury is kind of an interesting molecule that also gives rise to surface tension. It looks almost, when you put molecule on glass, it looks almost like water. It has a much, much higher surface tension, a 0.4, which is about, 5-6 times higher than that of water. It has no hydrogen bonds. And when you put, later on we'll talk about capillary rise, when you put a capillary into mercury, the interface of the mercury basically sinks down rather than goes up as you expect from water. Does anybody knows why? What is that? Yeah, but why is that? I mean, first of all, why mercury has this huge surface tension?
It's non-wetting fluid.
I'm sorry?
It's a non-wetting fluid.
Yeah, but it's a consequence. I'm trying to understand why.
Is it something to do with metallic bonding?
It is metallic bonding, absolutely. So it is metallic bonding that give rise to the high surface tension. It is a lack of hydrogen bonding that does not adhere, so the liquid does not adhere to the glass as water will do. So it will turn out that the hydrogen bonds of the water plays multiple roles in the behavior of water. One of them is the surface tension, which is really, if you wish, a cohesion between the molecules of water. The other would be the interaction between that water and, say, hydrogen silicate surfaces, for example, with hydrogen groups on the, not hydrogen, but it's actually OH groups on the surface that would allow the pooling or the wetting of these surfaces. So this is interesting, and that's a topic of the next item on the list of factors that affect the magnetic potential, and that's contact angle and wettability. So when we place a drop of water on a surface, several things could happen. The drop could curl up and become beaded like the droplets of mercury I showed you on the glass, or it can spread on the surface. The spreading will not continue forever. At some point, the drop will assume a certain shape. That shape represents the balance of forces that wants to pull the liquid or to spread the liquid, and the forces between the molecules of liquid that want to keep it together. This can be formalized, as Young have done in 1805, by writing this interfacial energy equation that says the increase in area covered by the water, and I have here three interfaces, or three surface tensions, if you wish. The solid liquid, the gas solid. So the gas solid is the surface before wetting. The solid liquid is the surface after the wetting by the liquid. And then there is the liquid gas, which is really the surface tension that I mentioned earlier. So what happened is that per unit area of covering the surface, converting a surface that was gas solid by solid liquid, there is a certain amount of area of stretching of the interface, which is really that same delta A cosine of some angle, which I'll define in a minute, times the surface tension. So in other words, this is the amount of increase in interfacial area of the air-water interface that is induced by this wicking or wetting of the surface. You can yeah?
I was always wondering how I should understand this energy that is in the gas-solid interface. What's behind that?
Oh,
I see the other two ones, but what type of energy?
so why is it that you see the fact that I have discontinuity in the lattice structure of any material? Why is it clear that it will give rise to some surface tension when it's a liquid and not when it's solid? After all, it takes energy to create this new surface, right? I take a surface, I take a piece of rock to break it and create two new surfaces. I have to invest a certain amount of energy. And that will be, not that, but it...
So that has nothing to do with the gas, it only has to do with something to do with the solids.
Yeah, but it is an interface. We identify it as the interface between the solid and the gas to separate it from the interface between the solid and the liquid, for example. Because the liquid is there, this attraction here minimizes the interfacial, minimizes the energy of the entire system of the drop. And that's really the key to what Young have done. But when he described this spreading phenomena at equilibrium, when there is no changes anymore in interfacial energy, you end up with this formulation that upon rearrangement give us the contact angle at equilibrium between the, at the contact line, between the solid, between the liquid and the air, the liquid and the solid, given by the difference in the interfacial energies of the solid covered with the, the solid uncovered with the liquid minus the solid covered with the liquid divided by the surface tension of the liquid gas. Okay, it's an equilibrium of interfacial energies. It has a geometrical consequence in terms of this contact angle, and it is a remarkable thing about this. It is defined on the molecular scale, yet it manifests itself at all scales, including macroscopic scale, and that's not so trivial. And people actually, you can measure it by looking at the droplets or other methods. Yeah, I added this little thing here just to say that it is a three-dimensional phenomena, and yeah. So this phenomena of spreading and creating a contact angle help us distinguish types of interaction between liquids and solids. Sometimes we call that when the contact angle is less than 90 degrees, we say that the liquid wets the surface. So the system is wettable, and we'll hear more about wettability later on this afternoon. In some cases, and you all have seen that on Gore-Tex or some other treated surfaces and sofas and whatnot, that water will bead on the surface. And then we say that the surface is non-wettable, or in the case of water, it's hydrophobic. Okay, so when you hear hydrophobic and hydrophilic, think of this wettability phenomena. Okay, so again, it is a phenomena that is not only involved the properties of the liquid, but also interaction between the liquid and the solid. The description here is quite reasonable when you look at flat surfaces, horizontal flat surfaces, homogeneous surfaces. When you see this same behavior on tilted surfaces, you'll see some more complex behaviors. I'll talk about two examples. One is when you wet a chemically heterogeneous surface, where I have volume fractions, or areal fraction if we wish, of materials of two properties. For example, if I have sand that is treated to be hydrophobic by salinization, 50% of the grains are made of hydrophobic and 50% of the grains are made of hydrophilic. So this will be a heterogeneous system, and you'll ask yourself, what will be the effective contact angle on that material? So according to Casey's equation, which is really a kind of operational equation, it suggests that the effective contact angle for this heterogeneous system will be the volume or the area fraction of the say the hydrophobic sand plus 1 minus that fraction of the hydrophilic sand. Together they'll give rise to the effective contact angle of that composite surface. So I gave an example with hydrophilic grains, sand grains, but you can think of grains and pores. So what's the contact angle of water with air? 180 degrees. So you can already imagine that you can calculate, according to Casey's equation, what will be the effective contact angle on a porous surface based on the porosity of that surface. The other phenomena that I'd like to point out is the fact that when you have a surface that is rough, that solid gas surface that needs to be covered by the droplet or by the drop in the previous treatment will be much larger, or be larger by a fraction that is the ratio of that rough surface to an equivalent projected smooth surface. And it turns out, according to Wenzel's equation, that the contact angle, effective contact angle over a rough surface will be roughly the ratio of this rough to smooth surface times the contact angle on a smooth surface, which is really a very useful result if you want to allow for a correction just for simple roughness. Okay, so this is the basic facility. The phenomena manifests itself in many forms. I mentioned the example of the hydrophilic sand. Here you have a fraction of the grains that are hydrophobic in a sand mix, and the effective contact angle that people have measured over that system. And you can see that the behavior is very well described by this Casey's equation that basically weighs the area fraction of the different sands. So this is one example. Another example that is now very well developed by, I don't know, car makers and so on to create windshields that don't hold raindrops. So this super hydrophobicity of surfaces by texturing the surface. So there is some manipulation, not so much of the properties. The properties of the surface are what they are, and also of the water in this case. But the wetting of the surface takes on a different form. In particular, the fact that as the droplet spreads, according to Young's equation, it should form a particular contact angle. But if you have a change in the geometry of the surface, there is a whole range of contact angle that could be formed between this contact line and the surface. This is from work by Kere. And basically, that gives rise to hysteresis, and so much so that you can actually manipulate, so droplets will sit on a surface that, other than their own weight, they'll be completely spherical, non-wetting the surface. Another phenomena, maybe of interest later on, is the fact that you can exploit wettability. In this case, they covered the mesh of copper with Teflon that will not allow water to pass because Teflon is non-wettable, but will allow oil to pass through this mesh in the system. These are just a few examples of how wettability could be engineered. And in fact, we are very late to this game. Plants have been, in the last 500 million years, have been perfecting this wettability manipulation so much that you have the lotus leaves, and in fact, almost any leaf will have features that take advantage of wettability, either by forming waxes that are hydrophobic or by creating a very clever textured surfaces to either repel water or roll water to collect dust over surfaces and things like that. Okay, so this phenomena is very common, very rich in the plant world, but also in butterflies and the insect world and so on. So,
examples in nature of
hydrophilic surfaces. I'm thinking that most silicate would be hydrophilic, falling under the definition.
In the world you're describing here, the plants,
yes, actually, I think there are. It is.
Dani,
Huh?
the reason why it's hydrophobic is you don't want the water to soak into the leaf.
Yeah, that's I
You
know.
want the water to soak into the roots, so the roots must be hydrophobic.
No. But there is this honeysucker. I mean, so there is there is a manipulation of the beak of honeysuckers to be hydrophilic, exactly to pick up that. Okay, so there are examples. Okay, so we finished with the surface tension, with wettability. I'm going down the list of the factors that affect emitting potential. I'd like to talk a bit about interfacial curvature, which is a really fascinating phenomena. It has been discovered simultaneously by Thomas Young in 1805, but also by Simon Laplace the same year. And the interesting thing, as the French-speaking here could tell you, that this is an addendum to a much more elaborate work about celestial mechanics. And there was a supplement on the theory of capillarity, which is kind of interesting. I don't think it will pass review this time and age. But basically, what these two have shown is a link between the curvature of the interface and the pressure jump that will happen between the liquid phase and the vapor phase or the gas phase. Just to illustrate how this works, I'll give this example of a bubble inside a pool of water of radius r, and I'm applying some work, applying some pressure, if you wish, to increase the volume of the bubble against the surface tension by the amount dV. And if I apply the geometry, the spherical geometry to this problem, I have the delta P dV, and dV would be basically a sphere, equal to surface tension times, at equilibrium, surface tension times the increase in surface area of that bubble. Dropping terms of second order out of the dr squared in this problem give us very simple algebraic expression that says that the pressure difference between the air in the bubble and the liquid pressure will be simply 2 times the surface tension over the radius of the bubble. The smaller the bubble, the larger the pressure difference between the bubble and the air. Okay? So that applies to, in this example, it's not so much related to porous media, but you can immediately see a situation in which you have these curved interfaces, say between in residual water held between grains of sand, for example. In that case, we have not a single radius, but a bit more complex surface. So we have in this pendular domain, we'll have one radius that tells us the curvature in this direction, and one radius in the meridial direction. And we need some convention to give this signs to this radii. And the convention is the following: if the interface bulge, if the water bulges into the air, the sign that I'll give to this interface will be positive. If the air bulges into the water, the sign I'll give to that radius will be negative. So I wrote this little icon here, and then I looked at it again today. I was thinking, okay, maybe it's a bit confusing. The basic idea is that the bulging of water to air will have a positive sign, not in terms of pressure in the liquid. Every time we're looking at the difference between the pressure in the liquid and the pressure in the air. So this will have a positive sign to the radius. This will have a negative sign to the radius. Okay? So for example, when we look at these two radii of curvature in a pendular domain, the R1 will have a positive sign, and R2 will have a negative sign. And that's how we'll define what will be the capillary pressure, for example, within this pendular domain. Is that clear? I know it's after lunch and the eyes are kind of... Okay. Just a comment. Yeah. Yes.
No, it's the other way around.
No, don't be confused by the icon. Forget the icon for a moment. I'm just giving this. This will be a negative sign. This will be a positive sign. All right, guys. Professors are not allowed to interfere during the lecture. Is that? This is not going to work this way. I want to make a comment that for many applications, this approximation of an interface by one radius or by multiple radii is an approximation to the actual interface that can be far more complicated. So this is attributed to Fischer. It's called the toroidal approximation. But the actual surfaces can be quite complicated, and you require some analytical geometric representation of these interfaces to describe them. So keep in mind that when we talk about things and just express them by radii, it is an approximation. It's a very good approximation, but approximation nonetheless. So that brings me to the capillary rise, which is central to the capillarity in porous media. And it is attributed to Jurin about almost 100 years before Laplace and Thomas Young. Jurin, who was kind of quite famous at the time, he followed Newton. Actually, he's holding in his hand this Principia, the manuscript of Newton. He was famous in London for developing some vaccines and so on. But one of the things that got his attention was a friend. So he said, it's exactly, I just copied it here so you can read. Some days ago, a method was proposed to me by an ingenious friend for making perpetual motion, which seemed so plausible and indeed so easily demonstrable from observation by the late Mr. Hawksby, said to be grounded upon experiment that, though I'm far from any opinion or of attempts of this nature. Remember, I was very, very careful. I was a good scientist. I don't believe in perpetual motion, but I simply could not understand why it shouldn't work. So basically, this is the setup that his friend was suggesting. Basically, take a capillary, stick it in water. Water will rise on the capillary, and if you bend it, it will drip back to the water. He was thinking, gotta work, right? Anyway, so in the same paragraph, at the ending, he said, but as searches after things impossible in themselves are frequently observed to produce other discoveries unexpected by the inventor. So he was completely reflective on the situation, saying, okay, I realize this is not going to work. By the way, why it shouldn't work? What? Yeah, but tell me why this shouldn't work. It's what? Form the drop, take energy, and it will actually dissipate the driving force for the pulling of the water and all that. But in any case, it was quite interesting. So the way we understand capillary rise today, basically we dip a capillary in water. Basically that water spontaneously being pulled by the same mechanism that we were thinking about the spreading of a droplet on the surface. As the water is being pulled, because of cohesion between water molecules, it pulls behind it a train of water until the weight of the water is equal to the driving force. And basically, we can rearrange this equation and calculate what will be the height of rise of this water in terms of the surface tension, the contact angle between the water and the material, in this case, say glass, gravity, and the radius. So the capillary rise, everything else held constant, is inversely proportional to the radius of the capillary. Smaller capillaries will have higher capillary rise than large capillaries. Is that clear? Okay. So now we can derive this capillary rise equation from at least 3 different formulations, from the Young-Laplace formulation of pressure. We can do it also based on minimization of interfacial energy. They all produce the same result, luckily, so we're okay. And that's basically this fundamental capillary rise equation. If you put the constant for water, it ends up being that the capillary rise is about 15 over the radius of the capillary in microns. So 15 over the radius of capillary microns give you the height in meters. So if you want to impress somebody in a bar, just do that. Okay. Questions? All right. So capillary rise, that is that basically is a culmination of the surface tension, the contact angle, the curvature of interfaces, is fundamental to our understanding of how water is held in unsaturated porous media. So much so that we take a very complicated pore spaces, we conceptualize them as if they were by some equivalent capillary, and all our science, all the stuff that you heard earlier this morning from Reen about hydraulic conductivity and so on, are all based on this conceptualization. You have to keep it in mind because it is very, very important that you don't fall into the trap of this formulation and start looking for cylindrical capillaries in rock or in soil. You're not going to find them. Nevertheless, this formulation or this concept allowed us to advance and make some quantitative predictions about capillarity in porous media. For example, if you tell me what is the grain size of, say, sand, silt, and clay, I can more or less predict how high the capillary fringe would be in the different materials. It's far from being perfect, but it at least places things in the order of magnitude or in the range that we observe. Most of the textbooks talk about capillary rise for cylindrical capillaries, which are as I said, a very special type of capillaries. But there is no reason for you not to develop understanding for capillary rise and water retention in angular capillaries. The physics and the geometry are simple enough for you to be able to make this transition. Just keeping in mind that angular capillaries, unlike cylindrical capillaries, may have coexistence of the liquid and the gas phase, whereas cylindrical capillaries usually behave like a piston. You have either the capillary is full or empty. So those are the primary differences between angular capillaries and circular capillaries. But otherwise, if you understand this phenomena, everything else is subject to the same physics as you can imagine. We can calculate, for example, you absolutely don't need to attempt to remember this slide. It is just to make a comment that I can calculate what is the saturation of a capillary of any shape, regular geometry, because otherwise it's a bit complicated, based on the ambient capillary pressure and some geometrical factor. That's it. So geometrical factors I can develop for any shape. You apply that, the radius of curvature that are associated with the metric potential can be described by, say, the capillary height, equivalent capillary head of gaseous or metric potential. And you basically have a way to express saturation of pores under different metric potentials. But I want to go back to the capillary rise and show some work of Bicot and Carré that was kind of surprising that only in 2002 people have presented this, where basically they look at capillary rise in a cylindrical square capillary by balancing the driving force, which is the perimeter times surface tension times the cosine of the contact angle, with the weight due to gravity in that capillary. So there is a primary weight is simply the area of the capillary times the main height of the capillary rise, plus some correction to the fingers. What do you think would be the correction to this story for capillaries of the orders of, I don't know, 50 microns? Is it 50%, 5%? This liquid held above this main. Anybody?
Should be a lot.
Give me a number.
50, factor of 50.
Okay, so it is actually 2-3% correction for most. Yeah, 1 over. Very good, Olaf. So basically, the rigorous solution, because of the geometry can be easily integrated, is given here. But for all practical purposes, you can use 4 times the area, which is basically the. Let me show it here. Yeah, so that the capillary rise will be simply 4 times sigma cosine of the contact angle over rho g times the side of the capillary. And these are the experimental data of Bicot and Carré, and the line is basically this line, ignoring the fingers because they're really not contributing that much. And you can take this to other complicated geometries like a bundle of cylinders, capillary rise between a bundle of cylinders. If you know the perimeter, the weighted perimeter, everything is completely easily calculated. Okay? Yeah.
I have a question because all your assumptions and your energy balance is based on the fact that your capillaries are vertical
Yeah.
perpendicular to your ground, like your ground force.
Uh-huh.
But how do you, like, do you take it into account when you calculate for porous media that your capillaries are not?
That's a very good question. In fact, this is exactly what's going to be in the next slide. No, but seriously, we do that on average, and I don't think it's a big, it is a conceptual step, but it's not a rigorous treatment. But we can solve for the capillary rise for any angle by basically having the sine of the inclination angle applied to the gravity term. So it's not a big deal, but it was a good question in the sense that it brings me to issues of dynamics. So far, we talked about equilibrium, capillary rise. Wow, okay. So far, we talked about equilibrium, but we would like to know how fast capillary rise happens, okay? To do that, we have to understand the interaction of different forces. So far, we balanced gravity and capillarity. To know how fast things happen, we have to look at viscous forces and at inertia. Okay? So, a question. I have here two capillaries, large and small, dipped in water. These are the equilibrium heights. Which one will arrive to the equilibrium height faster? The small capillaries with a high capillary drive or the large capillary with the smaller capillary drive? Okay, so who thinks the same time? Okay, who thinks the large one? Who thinks the small one? Oh wow, excellent. It's not so. So the answer is that the large one will arrive first. The reason is that sorry. The reason is that the rate of capillary rise involved, as I indicated, some other forces. So viscous forces that are reduced in the large capillary will basically contribute to its arrival faster to the equilibrium. Okay? So that was basically the basis behind the Washburn-Lucas equation for the dynamics of capillary rise. So far, we just balanced these two forces, and we have this classical result of capillary rise at equilibrium, no dynamics. What Lucas and Washburn did independently was to balance the capillarity with the viscous term. Let's ignore for a moment gravity and just make the capillary horizontal. Right? So I'm using the term x instead of h to kind of create a distinction. And what you'll find from the solution of this equation is that the advance rate of water penetrating the capillary, driven by capillarity, will be advancing at the square root of time. When I add gravity to the story, there is an analytical solution also. It's far more complicated, but still we have the square root of time dependency on the capillary rise. Okay? So that's the Lucas-Washburn equation. By Fries and Dreher from 2008, I like it a lot because it kind of tried to put some order into the timescales of what happens when you dip a capillary in water. What happens, when is Lucas-Washburn equation valid, when equilibrium arrives, especially what happens at the very early time. So at the very early times, I just dipped a capillary in water. I don't yet have length over which friction will take place. I don't have yet height that will oppose gravity. So there, inertia is a dominant force. And when you look at the behavior at short times, after I dip the capillary into water, the relationship between the height and the height is linear with time, not square root of time. And that gives rise to a velocity that can be very high. For, say, a radius of, say, 10 microns of capillary, the speeds can be of the order of 4 meters per second. This is not speeds of porous media, right? I mean, we have heard 1 meter per day. I mean, these are 4 meters per second. So it lives only very short time, but it is very important, and it's particularly important when we look at
the opposite. So there the thinner capillaries will go faster.
But only for that instance of time, yeah. So here is an example of introducing water into a micromodel. and where inertia is important, look at how the interfaces, if you can see here, oscillate when they penetrate. In other words, this is a hallmark of inertial relaxation upon penetration. So not to spend too much time on this, I just wanted to point out that the displacement of fluid fronts is nothing like the normal behavior that we assume governs the airflow, this Hadrous representation that you heard earlier today. When you zoom in on the process, it is a very violent process. Things coil and then all of a sudden jump. There are huge pressure jumps. The interfaces themselves move very fast. And in fact, it has been recognized by Haines back in the 1930s. We call this Haines jump. So in the minute I have left, I'll try and demystify a bit of, 4 minutes. That's even more. I'll demystify a bit of this Haines jump and try and develop a bit of understanding. Is it important or is it not? So one of the things that you recognize, sorry for this complicated figure, what we have here, we have a bunch of experiments in which we displace air or water displacing air, where we plot the velocity of the front, the macroscopic velocity of the front, versus the individual velocities of the jumps that took place at the front. This will be the one-to-one line if these two matched. But what you see is that the velocities at the interfaces are much higher. In fact, here is a better representation of these velocities. So these are just the jump velocities and their frequencies. And you can see that for front velocities of the order of, 1, 4, 8, or 16 millimeters per second, the jump velocities are a few hundreds millimeters per second. So we have a striking difference between the motion. So what you see as macroscopically as a very smooth motion of a front is actually driven by little engines that sit there, coil, and then boom, jump. And the collection of that, of course, is the macroscopic motion of the front. So this has some ramifications about our representation of the processes in that front. You know, there's nothing in the Buckingham-Darcy or other representations to account for these jumps that are, in some cases, easily enter into the inertial regime. So the energy dissipation and so on and so forth are not very well described by our standard models. To try and understand a bit more quantitatively about the role of inertia in this story, I want to be able to turn on and off inertia. Now, in experiments, I cannot turn off inertia. I can only turn off inertia in a model. So we build a model of a pore throat network in which we can simulate or compare outcomes with the inertial term and without the inertial term. And what happens is quite interesting, completely opposite to what we predicted, which is kind of a bit humbling.
Is this an experiment or is this a simulation?
It's a simulation. Only in a simulation I can turn off inertia. I cannot turn it off in reality, as you know. So I'm plotting here throat radius because my prototypic model has a different throat radii and interfacial jump velocities, which I can predict analytically with some assumptions without inertia. I can also do the numerical model without inertia. When I include inertia, all of a sudden I see a broadening of the jumps. So my thinking was, hey, add inertia, everything will go faster. But in fact, some go faster and some go slower. And of course, you should expect that because acceleration and decelerations are same sides of the coin. In one case, you'll have an interface that coils back and others that coils forward. So you have a broadening of the velocities, which was quite surprising. What we did find is that some pores that were not penetrated without inertia did penetrate with inertia. So this is the red area here. So that was kind of interesting. Unfortunately, my biggest drive for this study was, does inertia going to change the phase entrapment? In other words, as the front travels and if it has inertia, would it leave a different picture in the domain? And the answer was, unfortunately, not. So while this is a simulation domain. While the details without inertia and with inertia are different, the overall picture on the saturation, on the phase entrapment was absolutely, well, it was different but not significant. In other words, what inertia does, it adds another force and kind of, I don't want to say stochastic component because it is not stochastic, but it diverges the outcome from the stuff that would be produced without inertia in our normal modeling. But otherwise, we were not able to show that it made, yeah.
Did you try to turn off gravity or buoyancy?
No, actually,
When you create a big buoyancy kill and inertia or without inertia, no big difference. Maybe if you kill
it is possible. It is possible, but we have not done that. Yeah.
Those old experiments, slow drainage, which are well modeled by IP, that means that you can expect that inertia won't have an impact really on the final.
No, it is possible that we were a bit naive in expecting it. My thinking was, if Haines jump is so important, and it is inertial, it is inertial in nature. If it is so important, will it paint the residual phase left behind the front or not? It does. You can see that it has effect, but it. So then I missed the point. I'm sorry.
No,
Could you speak up a little bit?
May I repeat the question? If you do an experiment of very slow drainage, for example, so it's a globally really slow displacement but with Haines jump,
Yeah.
and that was modeled with IP,
Yeah, I know.
and well, there is clearly no inertia, right?
Yeah, but okay, I see the point. So.
People who compare the statistical properties of the phase
Distribution.
to what was observed in the experiment, and they found the same thing, either with gravity or without gravity.
Okay, but that's related to the question about the gravity.
Yeah, but either without gravity or with gravity.
Okay, so what Yves is saying that under slow drainage, in which you control the rate of outflow from the system, people have been modeling this with invasion percolation, and they did not find differences. I guess I'm repeating it correctly. Okay, I'm sorry, I got to move forward because I have to finish.
Okay, let's conclude.
Okay, so I want to make. Okay, then I want to make just 2 points about to sharpen the message of Rin from this morning about the soil water characteristic curve. One is that some of the parameters that Rin have shown earlier today has their interpretation in the shape of these curves. And I don't think he emphasized them enough. One of them is the bubbling pressure, is this inflection point here. Residual saturation he did mention, and the slope of this curve or the spread of the pore sizes is embedded in these parameters of lambda or n, lambda for Brooks and Corey and n of Van Genooten. So that was just a quick comment on that. The second quick comment is about the formalism that we use to take information from the soil water characteristic curve, deduce a pore size distribution, apply Poisson flow into this collection of pores to deduce the hydraulic conductivity. So that is basically what Rin have done, and in fact the success of the Van Genooten model was primarily in ability to do that analytically and use some model, in that case the model of Moalem, to do this prediction. So the point here is that there is a deduction of the pore size distribution based on the capillary rise equation that I showed you earlier, treating the material as a bundle of cylindrical capillaries, to which we apply Poisson with some little corrections to estimate the hydraulic conductivity when I gradually remove pores that have been invaded at that particular metric potential.
So Dani, what is then the macroscopic effect of these jumps? Is this important for solute transport or
Yeah.
Is it really relevant otherwise than just saying, oh, look how funny it looks like?
Well, that's what have been people doing since the 30s, looking and said, oh, okay, this is a curiosity, but nothing more. But in fact, it could be very important for mobilization of colloids. It may, because of the huge stresses it can apply on microbes in soil, it could actually be very important for survival of bacteria or other small organisms in soil. So I think, but for the big question that we wanted to answer about the phase entrapment, so far we have no evidence. So it is, it has a play in mixing probably in France, it has a play in dislocation of colloids and so on, but I did not see any effect on the entrapment.
So you would expect, let's say, that dispersion coefficients, if you believe in dispersion coefficients, are different at such a moving front than before and behind because of these very strong velocity fluctuations?
Could be, yeah. That there'll be stronger mixing than without including these motions, yeah.
You said there was numerous jumps that are being recorded. And I was just wondering, is there experimental possibility to record so many of them? I mean,
Yeah.
because people looked at pressure response,
Oh.
and it didn't look like
His
many
topic, his favorite topic. Branco, shut up.
So, yeah, well, there are ways, and Jesus will answer later. But yeah, there are ways to do that with fast cameras, with acoustic measurement, and also with pressure measurement. Nowadays, we can measure.
You've shown
Yeah.
pressure measurements.
Yeah, yeah.
What did we see?
What you see is fluctuations of the pressure at the bottom of the micro model
Okay.
that integrates.
That integrates.
Yeah, but if I measure at very high frequency, I can measure every jump in the front.
Because there was a kind of periodicity in the signal you
Yeah, because it is basically coil and jump, and that's a periodicity.
So that's not a noise. That's
No, it's not
something which
noise.
is
No, we use it.
correlated.
No, we use it to actually deduce pore sizes. If I know the velocity of drainage and I know the period between the signal, I calculate the volume, and that's another definition for us of a pore. So that's
Yeah, this suggests that a jump will initiate the next jump. This periodicity, where does it come from?
the periodicity comes from the fact that you have a range of pore sizes.
Using a constant pumping rate?
Yeah, I use constant pumping rate. Yes.
Characteristic pore size.
Yeah, here is the slide that I was looking.
My question is, where does it come from?
Here, let me explain. So this is experimental result here, in which you basically drive fluid through here. You measure fast enough, so you measure every pressure jump. So I have buildup of pressure, then in other words the coiling, and then a jump, and so on.
So that's not so periodic, right?
I'm sorry?
It's not so periodic.
No.
There is
Yeah, but it will depend. It will depend on the pore size distribution that I have in the system. So if I do it fast, if I do it slow enough, I can take this time between these events and calculate a pore size. And actually, it's no different than the geometrical pore size or the imaged invasion pore sizes. They are very, very close to each other, which is kind of surprising.
The pores jump one after the other, or does it happen that many pores jump at the same time?
That's the biggest problem. When you do it fast, you have cooperative pressure jumps, and then because I thought we can use it to characterize pore size distribution. No. When you do it fast enough, it doesn't.